Wait. Oh, hi. Didn't see you there. My name's Professor Chris.
I am Professor Sam.
And today we're going to be talking about more of the controversial theories of quantum mechanics.
Let's start with cats. I like that one.
This is Buddy. He's wearing cat ears. He's wearing cat ears in a cat box. See, you'd never expect Buddy to be wearing cat ears. Maybe he'd be in a box, but that's not till a few years after college. In the world of quantum physics, anything is possible.
We're using this example to describe the conundrum of the Schrödinger cat experiment. You see, Schrödinger's cat is a really interesting take on the uncertainty principle. When first proposed, it tackled one of the most confusing issues of quantum physics. Up until this point, people were certain that quantum physics had definitive answers, thinking it was a science of the absolute.
However, while in the macroscopic world this may hold true, when you shrink down to the levels of quantum physics, things become wildly unpredictable. Science becomes mere guesstimation, a measure of the probability of an event, and nothing more. In this world of the tiny and trivial, possibility is the only answer. In this universe, one could be... Alright, I think it's time we check back in on Buddy and see how he's doing. Why don't you come with us?
Buddy? Buddy? You doing okay?
Notice, Buddy is entirely encapsulated by the box. He's not responding to our calls, so we have no way of knowing how he's doing short of removing the box on top and checking to see for ourselves. Once we do that, however, we'll have a definitive answer, right?
Meow.
Wait, did you see that? Buddy was dead and alive at the same time. Enter Schrödinger's cat. In the Schrödinger's cat thought experiment, Schrödinger designed an absolutely absurd situation to describe the issue he had with the current view of quantum physics. The experiment, detailed in his own words, states that
one can even set up quite ridiculous cases. A cat is penned up in a steel chamber, along with the following diabolical device, which must be secured against direct interference by the cat. In a Geiger counter, there's a tiny bit of radioactive substance, so small that perhaps in the course of 1 hour, one of the atoms decays, but also with equal probability, perhaps none. If it happens, the counter tube discharges and through a relay releases a hammer, which shatters a small flask of hydrocyanic acid. If one has left this entire system to itself for an hour, one would say that the cat still lives if meanwhile no atom has decayed. The first atomic delay would have poisoned it, resulting in its death.
Whoa, okay, Schrödinger, let's slow this down a little bit for the rest of us. Okay, so some poor cat got coaxed into a box. Inside this box is substance with a half-life of 1 hour and a Geiger counter to detect whether or not the atom has decayed. If the atom has in fact decayed, the Geiger counter would set up some sort of Rube Goldberg-esque contraption chain reaction, causing a hammer to break a container of hydrocyanic acid, effectively killing the cat. However, if the atom has not decayed, the cat will escape unharmed. Remember, there's a lid over the box the entire time, so until that lid is removed, the cat may as well be dead and alive at the very same time.
You might be starting to realize that this situation is ridiculous to the point of hilarity. That's completely on purpose. See, Schrödinger was confronting the triviality of some of the proposed answers to the newly developing field of quantum physics' biggest questions. However, he clearly saw that pursuing a definitive answer was beyond ridiculous. Quantum physics is a field of probability. Just like the electron cloud model describes the chance of an electron being found within this range of a nucleus, things at the microscopic level cannot be effectively determined.
Consider the task of attempting to locate the position of a subatomic particle. To view this particle, you have to bounce a photon off of it. However, once you bounce that photon off of the particle, you have altered its trajectory, changing its location. This is not in fact where the particle was, but where it is now. Through usage of various equations, such as Schrödinger's equation, we can calculate the probability of a subatomic particle residing in a particular area of space, but never its true location.
Quantum physics is as much a revolutionary science as it is an evolutionary science. Assertions are dynamically developing, Viewpoints are radically revising, and theorists are adopting newer techniques, more accurate assumptions, and discovering more absurd realities than you could possibly imagine. Welcome to the world of quantum mechanics.